a look at a couple more examples of finding the area of regions bounded by curves. So in this particular example, I've already brought over the graph of this particular example because I wouldn't necessarily expect you to know one of these graphs. One is a line, but the other one, the x times e to the negative x squared, might not be something we know how to graph without a graphing utility. So I use Desmos. And if we want to find the area of the region that is bounded by y equals x times e to the negative x squared, that's this graph, the kind of the little loop-de-doo down here on the bottom, and y equals x plus 1, so that's just a line, y-intercept of 1, slope of 1. And then the two vertical lines, x equals 0 and x equals 2. So you can see all of those in the drawing right here. Here is the line x equals 2, and here is the line x equals 0. All four of those pieces, I actually brought it over with the shading as well, but it says find the area of the region that is bounded by those four graphs. So it's the region inside of those four graphs that we have graphed here. So if we want to find that area, we're going to use our formula, the formula we derived in the first video for this section. So we're going to find the area by taking the integral from a to b of f of x minus g of x, where what I didn't write here, but this formula explicitly states where f of x is greater than or equal to g of x for x in the interval from a to b. So that's where we came up with, in the last video, this little shorthand notation, this y sub t, meaning the function on the top minus the function on the bottom, where we're calling f of x our function on the top, and we're calling g of x our function on the bottom, just to give them names. So g of x is the function on the bottom, f of x is the function on the top. So when I'm looking at this and getting ready to set up this particular problem, we would want to denote which is the function on the top, which is the function on the bottom. And sometimes in the region, it can be helpful to draw a little rectangle. Remember, these areas, this formula comes out of a Riemann sum. So if we think about, okay, we came up with that integral formula by looking at areas of rectangles and summing them all up. That just disappeared. That's kind of funny. And summing them all up. So we were looking at areas of rectangles. And in this case, you can see with that rectangle right there, which of those functions is on top. And it might seem obvious, but sometimes it can be helpful to draw that rectangle and visualize which function is the function on top and which is the function on the bottom. So make sure we're setting up our integral correctly. Okay, so I think we got the functions on the graph. Let's zoom out just a little bit and we'll get our formula going here. So our area is going to be, actually I'm going to have to zoom out a little bit further. Our area formula, we'll get it set up and then we'll zoom down here to the bottom so we can see the graph. It's going to be the integral of the function on top, so that's x plus 1, minus the function on the bottom, so that's x e to the negative x squared dx, and we're integrating across the bound, so we start drawing our rectangles, adding up our rectangles, starting at 0 and adding them all the way up till we get over here to 2. It's kind of sloppy, but you get the general idea. So we're integrating, slicing up that area from 0 to 2 and calculating the area. Now, at this point, we just have some integration to do. So let's go through this integration. The first two terms are just simple integration formula. So we can integrate x, that becomes x squared over 2. We integrate 1, that's just x. Now we still have to integrate x e to the negative x squared dx. Now that's not one of our basic integrals, so I'm going to highlight that and we'll look at that. We're going to have to use substitution actually on that one. So we'll come to that one in just a second, but this is a definite integral, so I'm going to get it totally integrated first, and then I'm going to evaluate it from 0 to 2 to find that area. So let's look at our highlighted piece right here. If we're going to use substitution here, because I see that this exponential function has a function of negative x squared up there. I think that's a good idea. So if we let u equal negative x squared, then my du dx is negative 2x. Separate the differential right there so we can isolate du. And then I see that I've got an x and a dx. Let me write it one more time. carry those other terms over, just x squared over 2 plus x minus, I'm going to write this as e to the negative x squared times x dx so we can see the substitution. Now you might not have needed to do that. Hopefully by now we're getting pretty good at substitution. Divide by negative 2 and we get negative 1/2 du. So negative 1/2 of du is equal to x dx. And now I can make those substitutions. So there's the x dx. There's the negative x squared. I'm going to make the substitutions. So this becomes minus the integral. I'll carry those other terms down just a second. This becomes minus the integral of e to the u times minus 1/2 du. Now that minus 1/2, I'm going to pull out to the front, so we get positive 1/2 integral of e to the u du. Substitution has turned my integral all in terms of u, and it is now a function that I can integrate. So the integral of e to the u is just e to the u. So that term becomes just 1/2 e to the u. And I'm going to go ahead and plug my u back in. So my u, remember, was negative x squared. So I did 2 steps at once right there, but hopefully we can see it all. And now I'm going to carry, I didn't want to rewrite those over and over again. So now I'm going to carry those other terms that we had already integrated, dot, dot, all the way down here, x squared over 2 plus x. And we're evaluating that from 0 to 2. So now we apply that fundamental theorem. We'll plug in 2, so we get 4 over 2 plus 2 plus, we get 1/2 e to the negative 4th, and then we're subtracting, we get 0, 0, and 1/2 e to the 0, which is going to become 1/2. And this ends up being 4 plus 1 over 2e to the 4th when I drop that negative exponent, plus 1/2. So let's see. Oh, I'm sorry, minus 1/2. I lost my negative right there. Minus 1/2. So we've got 4. So that becomes 8 over 2 minus 1/2. 7 halves plus 1 over 2e to the 4th. And that is my answer. Now, just because we are actually talking about area, it might be a nice little idea to put back in units squared. Those are square units of area between this curve. Now, the next example is popping up there on the screen on the right, and we'll do that example next, but let me get that all the way on the screen so you can see the whole thing. So we figured out how to set up the integral, then we integrated, had to use a little integration technique in there with some substitution, and then calculated the integral. So we had to use a little substitution right here, kind of bringing some concepts together on that problem. All right, let's take a look at the next one. So let's take a look at this example. And this one's going to take us, I'll talk about that generalization in a second, but let's see why we need that first. Let's graph this function. So this one I didn't graph. This one has 2 functions, y equals the sine of x and y equals the cosine of x, between the 2 vertical lines, x equals 0 and x equals 2 pi. And we want to find the total area of the region that gets bounded by those 2 functions. So let's draw those functions. So these are functions we should be able to draw. So the sine graph, we want it just from 0 to 2 pi. So sine graph is going to look, let's get my key points here plotted, and then I'll put the curvature in. Oops. All right, pretty good. Obviously that keeps going, but we only want it from 0 to 2 pi. And then I'm going to draw in red. I'm going to draw the cosine. So the cosine graph, I'll plop in my key points for the cosine graph, plot those in there, and then add in some curvature here. Trying to make it a nice clean graph. And then we are looking at it. So we'll put in a little line here from at x equals 0 and at x equals 2 pi. And we want the area of the region enclosed, bounded by those curves. Now here's something that happens that's kind of interesting, and I'm going to draw in 2 different ways. Notice this first little area right here, the cosine curve is on top. And then on the next little region, It flip-flops. The sign of x is on top. So remember, when we're finding area, we have to determine which function's on top and which function's on bottom. And then in this next little piece, the cosine is back on top. Let's write y equals cosine of x. And I drew them, but let's also label them. And I drew them in different colors so it was easier to see. So if we want this area, we actually are going to have to break it up into the 3 different regions and calculate the area of each of those regions. So remember our formula from before. I'm going to go back to that previous page where I had written it. Remember this formula that we were working with up to now for calculating areas of regions has this specification that one of the functions is always on top. Well, what happens if the functions flip-flop and one is on top for a portion of the interval and another is on top for another portion of the interval? How do we deal with that? And that's the exact scenario that we're looking at right here. So how do we do that? Well, what we're going to do is we're going to generalize our formula. And the formula, if the 2 curves that are bounding the region, if they happen to switch, so if it happens to be that the functions intersect and one, they flip-flop, one is on top to begin with and they intersect and then the other one goes on top, becomes larger than the first function, then what do? Well, this is what we can do. We can calculate the area by taking the absolute value of the difference. So let's highlight that. Now, what does that mean? Well, in practice, we just simply take the specific formula for the absolute value. We take the absolute value as a piecewise function. It is defined to return back itself if what's inside is positive, which is when the f of x function is larger. So when f of x is greater than g of x, then the absolute value just returns back f of x minus g of x. And when g of x is bigger, the inside of this absolute value, the difference would be negative, and so it returns back the opposite. It flips the signs, and we get g of x minus f of x. So that's the specific formula if we're looking at a region where the functions will flip-flop, meaning one will go on top at different portions of the interval. So how do we do that? Well, what we do in practice, in order to apply this, we have to figure out where they actually intersect, and then we have to break up the integral into separate pieces, into separate integrals. So let's see what that looks like. So I will, let me take off the highlighting, and I'll let you, if you want to screenshot that or write that down. That is the generalization. But in practice, what it means is we have to figure out where they intersect and then determine on each individual interval which function is on top, so we can set it up properly. So let's take a look. So first, let's figure out where are these intersection points, because clearly these 2 graphs are intersecting. So where are the intersection points? Well, when does the sine of x set the 2 curves equal to each other? When does the sine of x equal the cosine of x? And there's a few ways to think of that. You could go to the unit circle. I'm going to kind of do more of a trig equation approach here. Divide both sides by the cosine of x, and then I find that the tangent of x equals 1, and then I'm just going to use some inverse properties here. The tangent of x equals 1 when x equals pi over 4 plus the period of tangent is pi times some any integer k. So that is the solution for all of the places. Since we want it only on the interval from 0 to 2 pi, we're going to be looking at x equaling pi over 4 and add pi, 5 pi over 4. And so those intersection points, let's put them on the graph. Those intersection points right here and right here, we'll even circle them so we can see those intersection points. Those intersection points are at pi over 4 and 5 pi over 4, where the sine of x and the cosine of x intersected each other. So first we find the intersection points, and then we have to set up the integral. So the total area of the region is going to be equal to, well, there's 3 areas here. Let's go ahead and label them. This would be area 1, This will be area 3. I'll put those in red since the cosine is on top on those. And this is area 2. So when I'm setting this up, this is going to be the integral. The first region is going to be the integral from 0 to pi over 4. And on that region, the cosine curve is on top. So it's going to become function on top is cosine minus the function on the bottom is the sine of x to find the area of that region. Then I have to add up. So that was region 1. Now I have to add up the second region. And to find the area of the second region, where the sine function is on top, we take the integral from pi over 4 to 5 pi over 4. This time the sine of x is on top, and subtract the cosine of x, function on the bottom, dx. And let me scoot this whole thing down. And we'll keep going. And now the integral, the last portion, is the area from 5 pi over 4 to 2 pi. And on that region, the cosine of x is back on top, and subtract the sine of x dx. And then that is the third area, corresponding with the third area. And now we just have to actually calculate each of those integrals. So let's speed up the video, and we'll just do the calculations real quick, and we'll see what we end up with. Okay, and there we go. So I just sped up that video there, do the calculations, take the integral, plug in the bounds, evaluate, and we calculate out, and we get 4 root 2. Now again, that is in units squared because we are talking about the total area. So what we did right there, let's try to get it all on the screen. What we did right there, remember, this was the sum of all 3 regions. So this was the sum of 1, 2, and 3. And we had to calculate each of those individually. There was some definite symmetry on this particular one. And you could use, obviously, with sine and cosine, there is symmetry. We could have used a little bit of symmetry and kind of played around with the bounds and where the symmetry is. But I won't get into that. I just wanted to mention it here at the end of the video. What I wanted to illustrate here, though, is when we have to find area between curves, and if one function is not always on top, if the functions flip-flop to which one's on top, which one's on the bottom, we got to find those intersection points and break up the integral into separate integrals.